Hello everybody and welcome back. In this video solution, we are going to dive into the problem find minimum in rotated sorted array part 2, recently asked in Facebook. I'm going to discuss the binary search optimization in detail with the help of a couple of visualizations to help us understand what's going on. Let's get started with the solution. So let's get one solution right out of the way. Since the goal is to find the minimum element in the rotated sorted array, one very stupid solution is to just return minimum of A. Go ahead and submit this and you will find it gets accepted. Pretty simple, we're done, right? However, this is not best solution. Like, you can write this in an interview and the interview will most definitely ask you to optimize that. Now, how do you think about that? One thing to note is that this minimum of A is going to take order of n in terms of time complexity. Can we do better? Can we bring it down to say order of 1 or maybe order of log n, something like that? Well, the entire solution hinges on this one keyword, sorted. The thing is, we are given a sorted array, and so it should make you think about binary search. In fact, that is one of the core observations leading us to the solution. We have to think in terms of binary search. But of course, the question is a hard labeled question and it's, well, not a direct implementation of binary search. That's because of this another keyword saying that the array is sorted but also rotated. And what it means is we have a visualization like this. So we have a sorted array and starts from say some value 2 over here, then it goes up to value 3, then 4, something like that, and then it goes up to all the way up till 10. But the thing is, it's rotated now by a couple of steps. So what this would have been the start is not actually the start anymore. The array has been shifted by whatever is the amount between this yellow left line and the green middle line. Okay, that's the general setup of the question. Now, how can we start to think in terms of binary search? The first thing I'm going to do is write down the very basics of binary search. So we have something to start off with. I'm going to remove this and I'm going to write this. Okay, what is this? First, we get out the left and right pointers and we iterate while left is less than right. This is exactly the same as the official implementation. In fact, most of the solution is borrowed in structure from the official implementation. Links down below if you are interested. Anyways, first we figure out the mid, and then if the mid is lesser than the x, which is the target element, we're going to do r equals to m. If the middle is greater than the x, we're going to do middle plus 1 as the L. If both of them are the same, if array of mid is equals to x, which means that we are looking at the exact element we want to search, then we're done. But the thing is, this assumes the existence of x. X is in fact something we have to find in this question. We are not looking, this is sort of the question where we know we have to do something, we know we're looking for something, but we don't know exactly what we're looking for. In standard binary search, you know that you are exactly looking for the element x. In this case, we don't. But we still know we have to go somewhere in the direction of binary search. So how do we go about that then? Well, let's look at this solution. Let's look at this example. And this, by the way, is the only example you will need to understand all of the nitty-gritties of this question. So let's get started. The first thing we'll do is insert left and right pointers. So right points are the rightmost element in the array, left points are the leftmost element in the array. We can figure out mid by just doing L plus R by 2. What do we see right here? What do we see right away? We see that this middle is between, the answer is between this left and this middle over here, which means that all of the area between middle and right is of no use to us. So one possible condition is, this is what we have right now, is saying that, you know what, if M, which is the middle element, which is this current element, is lesser than L and M is lesser than R, then R equals to M. What it says is, if this array element is lesser than both the L and R, then we have to set R equals to M. Let's actually write it down. We'll say that, you know what, array of M should be lesser than array of L and array of M should be lesser than array of R. And if that is the case, you can do R equals to M. It's fine. Already starting to find out something. Let's keep on going. Okay, so what we'll do now, we'll set R equals to M. So the R will come over here and the M will move somewhere else. So this is what happens in the next iteration. Now, what do we see again? The answer is between M and R, right? So we have to move in this direction. We have to somehow cancel out the area between M and L. How do we do that? We can set L equals to M plus 1. If M is greater than L, if M is now greater than L and greater than R, then we have to shift L and we'll do L equals to M plus 1. So we'll modify this condition's elif case to be saying that, you know what, if this is greater than area of L and area of M is greater than area of R, then do L equals to M plus 1. Don't get too excited. We still have some more work to do. Let's keep on iterating. Let's keep on finding. So what will happen now? L will move in the place of R. L will move in the place of M. Okay. What happens in the next iteration? L is here, R is here, and M is here. What is the condition now that we can follow? We've already written on the condition. Which of them is the correct one? That's right. Is the condition 1. It says that if M is both lesser than L and R, then we can do R equals to M. So let's do that. Great. So this is now what we are at. Now what do we see here? In this case, M is lesser than L, but it's equal to R, right? Both of them are at the same level. What do we still know? We still know that the answer is between L and M, which means that we want to cancel out the area between M and R. So we have to follow condition 1, but condition 1 says M is less than R. Now that condition is no longer true. We can just remove it entirely and say that, you know what, let's forget about R entirely for this case and let's just look at L and M. Now if M is lesser than L, we can do R equals to M. So what we'll do here is remove this condition. We are no longer comparing M to R in this case, we're just comparing M to L. Okay, we're getting somewhere, Let's keep on going. So in this case, R equals to M again. So R will move over here. Okay, now what about, well, we have R and L again, so we can find out the middle. And what happens now? Similar to what we saw previously, what happened is M is greater than R, that's for sure. So we are looking at sort of the condition 2, where we want to move in the right direction now. We want to cancel the area between L and M. But the thing is, M is equal to L. So M is greater than L condition is no longer followed. So this is the useless one in this case. And we can convert it to M greater than R. So basically remove M greater than L condition. So we'll remove this condition over here. And we're good to go. Okay. What will happen in the next step? L again moves to this point. And so on and so forth. You will realize that the L, M and R will both, all of these three will come in this little area over here, little area at the bottom. Couple of iterations happen and this is what we have now. This is the zoomed in version of what we can deal with. Now what do we see now? Well, we still want to move in the leftward direction. We see that still the answer is towards the leftward direction. How do we get to that point? One possible way is to move the R by 1. And this is this condition over here, right? We no longer have any of these conditions being followed. Condition 1 or condition 2 no longer followed. All of them are the same level. What we can do is do R minus equals to 1. We can shift R by just a slight bit, So we can do R equals to minus 1. R minus equals to 1. Okay, what does this mean? This means that the R will start to push in this direction. It will start to push towards the green point that we want to get. And once we are at that point, what would happen? At that point, we have sort of exited the while loop. This will, there will be a condition where L equals to R. And at that point, L, R and M are both, or all of them are at the same point. And at that point of time, we can exit from this loop. And we can return array of L as the answer. Let's do a quick sanity check. And we'll go ahead and submit this. Cool. So we get a runtime of 52 milliseconds, which is faster than 80% of the people. Don't focus too much on the runtimes. They are very inconsistent, as you can see from the previous announcements I had. Anyways, yeah, this is the solution to the problem, find minimum in rotated sorted array. Now, if you're still around for this time, well, I want you to think about the time complexity. The space complexity is still quite trivial. Only thing we're storing is this L, R, and N pointers. So space complexity is order of 1 worst case. But what about the time complexity? Binary search gives order of log n complexity. But we have this single line over here, which is going to make all the difference. Now, if you're interested, this is sort of the case we are looking at, and you can pause the video right now and start to think what would happen in this kind of case. Now, if you're interested, you can go and look at the complexity analysis for this solution in my blog post, links down below. Anyways, this is it. If you like this video, give it a thumbs up. If you want to see more of these high quality visual solutions and good approaches to how to tackle these kind of problems, subscribe. And as always, thanks for watching.